Let's say you have $20 milligrams in your body, and I didn't say 20 milligrams of what. And that's at noon. If the medication is metabolized in such a way that half of it's gone after 6 hours. Then what is we'll call it A of T. The amount after T hours. Okay, well, it's always a good idea to sketch a graph. So let's say here is 20 milligrams. And here's 10 milligrams. And let's say that this is 6 hours. Then I know that my amount drops from 20 milligrams to 10 milligrams in 6 hours. I also know that this curve has the shape of a decreasing exponential. And cheating a little bit. Maybe that curve looks something like this. So A of T is a decreasing exponential, meaning I can say that A is A0 times e to the kt, that e to the kt that we looked at just a little bit earlier. We want to evaluate A0 and K. Okay, well, we know that we have 20 milligrams at T equals 0. So we can say that A of 0 equals 20 milligrams. Also, A of 0 equals A sub 0 e to the k times 0, because A of 0 Well, A of t equals A0 e to the kt. A of 0 equals A0 e to the k times 0. So A0 times e to the k times 0 equals 20 milligrams. But this is just A0 e to the 0 equals 20 milligrams. E to the 0 equals 1. So A0 is 20 milligrams. Okay, so we've evaluated A0 immediately. We want to evaluate K. Well, A of 6 hours is 10 milligrams. A of t is A0 e to the kt. So A of 6 is A0 e to the k times 6. And it's not 6t, it's 6k. Well, A0 is 20 milligrams as we found it, so now we know that $20 milligrams times e to the 6k is 10 milligrams. And I'm running out of room, so I'm going to have to bunch things up a little bit. Well then, e to the 6k, if you divide both sides by 20 milligrams, you get a half. If e to the 6k equals 1/2, then we can express this in natural log form. And this tells us that 6k is the natural log of 1/2, and the natural log of 1/2 is pretty close to 0.7. And you kind of remember that, it comes up a lot when you're doing half-lives and stuff. So that K is approximately equal to 0.7 times 1/6, which is about 0.117. So now we've got K. And also the natural log is not of 1/2 is not 0.7, it's negative 0.7. So K is negative 0.117. And we conclude, move this over a little bit, now that A is now 20 and we're going to understand that that's in milligrams, times e to the negative 0.117 t. This is approximately equal to, first of all, it's equal to 20 times e to the negative 0.117 raised to the t. That's 20 times 1 minus 0.117 approximately, because of what we did before. And you can think, okay, we'll use the Taylor expansion, but since we don't understand that, we just understand that there's a reason that it's equal to this. And that would be 20 times 0.883 raised to the t. Several ways of expressing this. This is a little more intuitive than this e to the negative 0.117 t, because you just have your base and your power, and you multiply that by 20. So this is a b to the t for b equals 0.883. You multiply that by 20, and you have it. Okay. So now, if you want to calculate how much you have after 12 hours, you can just take 20 times 0.883 to the 12th and figure out what it is. You can model the amount of drugs in your system then by saying, okay, if I take this medication every 12 hours, the first time I take it, after I take the medicine, say an hour after I take it, I got 20 milligrams in my body. Okay, well, the second time I take it, 12 hours later, I'm already going to have, turns out, 5 milligrams in my body, and I take the 20, and now I have 25. So now the amount over the next 12 hours would be 25 times 0.883 to the t. Well then, that would bring me down after 12 hours, that's going to bring me down to about 6¼ milligrams. So I'd have 26¼ milligrams the next time, and I would do the same thing with 26¼ I would eventually and actually exponentially approach some maintenance level of the drug in my body. And that's the reason. Those are the models that medical science can use in certain circumstances to calculate or estimate maintenance levels of a drug. Now, having said that, what happens in your body is a little more complex than this model. I don't know the details because I'm not a medical person, I'm not a biology person. There are all kinds of things. You have different enzymes acting in your body and different pathways, chemical pathways, and so forth. But this is based on the idea that the rate at which you change the amount of drugs in your body, the rate at which you metabolize those drugs, is proportional to how many drugs you have in your body. So if you've got twice as much of this drug in your body will be twice as active in metabolizing it. So it's an important model. It gives us a good approximation in certain circumstances with certain medications, with people in certain states of health. Okay. Medicine's a messy science. Biology is a messy science. So this model is not something you want to take lightly. You don't want to just assume it's going to happen. You want to do experiments and see how things progress and whether you do have this half-life. But a standard thing that you have with drugs is you do have the half-life. Okay. Okay, for any drug you can look up its half-life, or for almost any drug I've ever looked up. You look up its half-life, and you can then model what happens after you take the drug. So it's a very important and very neat model.